A galvanic cell or voltaic cell is an electrochemical cell that converts chemical energy of spontaneous redox reactions into electrical energy. In any voltaic cells, the components of each half reactions are placed in a separate container which consists of one electrode dipping into an electrolyte solution. The two half cells are joined by external circuit and the voltmeter measure the voltage generated. This is an example of voltaic cell based on zinc-copper reaction. In the anode half cell, which is the negatively terminal electrode, an oxidation reaction occurs as the two electrons from zinc atom move through the zinc electrode as the zinc 2 plus ion enters the solution. In the cathode half cell, which is the positively terminal electrode, a reduction reaction occurs. The two electrons reduce the copper 2 plus ions into the Cu atoms. After several hours, the zinc anode becomes thinner and the copper cathode becomes thicker. The charges of the electrode are determined by the sources of electrons and the directions of electrons flow from the circuit. In these cells, zinc atoms are oxidized at the anode and are the source of electrons. The electrons flows from left to right through the wire to the cathode. As the cell operates, electrons are continuously generated at the anode and consumed at the cathode. Therefore, anode has in excess of electrons and cathode has a deficit of electrons. That's why anode is a negative terminal electrode while cathode is a positive terminal electrode. A cell cannot operate unless the circuit is complete. The oxidation half cell, initially containing a neutral solution of zinc 2 plus ions, but as zinc atoms in the electrode lose electrons, the zinc 2 plus ion that form enter the solution and increase the concentration of the zinc 2 plus. This would give a net positive charge. Similarly, in reduction half cell, the initial neutral solution of the Cu2 plus ion would develop a net negative charge as the copper 2 plus ions leave the solution and form the copper atoms. Such a charge imbalance between the half cell would stop the cell operation if it allowed to occur. This situation is avoided by the use of the salt bridge. The salt bridge joins the half cell and acts as a liquid wire by allowing the ions to flow through both compartments and complete the circuit while keeping the electrolyte solution neutral. The salt bridge is an inverted U-tube containing non-reacting ions such as K plus and Cl minus dissolved in a gel which does not flow out the tube but allows ions to diffuse into or out of the half cells. To maintain a neutral oxidation half cell, as zinc atom converted into zinc 2 plus ions, the chloride ions move from the salt bridge into the electrolyte solution and maintain the neutrality of the oxidation half cell. As the copper 2 plus ions change to copper atoms, the K plus ions from the salt bridge move into the copper solution and maintain the neutral reduction half cell. The electrodes in this cell are active because the metal themselves are components of the half reactions. As the cell operates, the mass of the zinc electrode gradually decreases as the concentration of the zinc 2 plus in the anode half cells increases. At the same time, the mass of the copper electrode increases as the concentration of the copper 2 plus ion in the cathode half cell decreases. However, there are no reaction components that can be physically used as an electrode, so inactive electrodes are used. Most commonly, inactive electrodes are graphite or platinum. In voltaic cell, based on the following half reaction, the reacting species cannot be made into electrodes. So, each half cell consists of an inactive electrode immersed in an electrolyte that contains all the reactant species involved in that half cell reaction. In the anode half cell, the iodide ions are oxidized to solid iodine and the released electron flow into the graphite electrode and through wire. From the wire, the electrons enter the graphite electrode in the cathode half cell and reduce the MnO4- ions to Mn2+ ion. There are certain consistent features in the diagram of any voltaic cell. The two electrodes are immersed into an electrolyte ions connected through wires that is attached to a voltmeter. The electrode name, anode and cathode, and charge are shown. By convention, the anode half cells appear on the left. The electrolyte ions with its concentration are shown. The direction of electrons flows is from anode to cathode. Nature of ions and the direction of ions flow in the salt bridge are shown with cation moving to the cathode half cell while anion moving to the anode half cell. The half cell equation for this reaction is written as anode as oxidation process, where in this case zinc is undergoes oxidation by releasing two electrons to form the zinc 2+ ions. While at cathode, which is the reduction process, involving copper 2+ ions, is being reduced by gaining two electrons to produce the copper atom. The overall equation, okay, so we have to add up these two equations, equalize the electrons, okay, so that we can cancel it out. The overall equation is written as zinc solid plus copper 2+ ion produce zinc 2+ ion and copper solid. A useful shorthand cell notation describes the components of a voltaic cell. The key parts of the cell notation are as follows. Anode is written on the left and cathode is written on the right. A single vertical line represents the phase boundary to separate the components with different phase, while a double vertical lines represent the salt bridge, indicates the half cell are physically separated. A comma is used to separate the components in the same phase, while electrodes appear at far right and left of the notation. The cell notation for this zinc-copper reaction is zinc solid as our anode electrode, separated by a vertical single line, which is our phase boundary. And then we have zinc 2+ ion, aqueous. Since the concentration is 1 molar, we put it as 1 molar. And then we have a salt bridge, okay, to separate our two half cell, okay. And then for cathode, we have the copper 2+ ion, okay, the concentration is 1 molar. And it is separated by a phase boundary, and then we have our copper electrode. Another example, if we have an inactive electrode like this, so we have a graphite as our anode electrode, separated by, okay, from our half cell we have iodine, aqueous, and then here it is 1 molar. And then it forms the iodine solid, so aqueous to solid, we use again a phase boundary. So we have iodine solid, and then this two is in our anode half cell. Okay, so separated these two cells by a salt bridge. Okay, and then we have at cathode MnO4- aqueous 1 molar. Since we have H plus also in aqueous, okay, use comma to separate it. So H plus aqueous 1 molar, and it produce the Mn2+ ion. Okay, again same phase, comma, Mn2+ aqueous 1 molar. I'm so sorry, this is not solid. It is aqueous, right? And then we have H2O. Okay, so from aqueous to liquid. So H2O, liquid, and then we have our graphite electrode. Okay, so remember the stoichiometric coefficient is not written in our cell notation.